Radioactive, Decay, and Half-Life. Here's your joke for today. Don't trust atoms. I never trust atoms because they make up everything. Alright. Sorry, that was Brian.
Wow.
Is it supposed to be funny?
Yes.
I think my jokes are funny. I scratch that. I know my jokes are funny. You just don't have
not
a sense of
everybody
humor.
else.
I have a sense of humor.
Alright, we're going to unpack that reading you did last week with radioactive decay. First piece of candy for today tells me somebody who knows the 3 types of radioactive decay. Caden.
Alpha,
And?
beta,
And?
ooh, the whole gamma.
Gamma, fantastic. Ready?
Making
Alright. My throws might be a little off today because my shoulder legitimately hurts. So just be prepared for that. Okay. Reactive decay, we're going to unpack alpha, beta, gamma, and then we're also going to look at the mathematical model of those types of decay. Okay. Yeah, Alex?
May I borrow a pencil?
Sure.
Did you write all of that?
These are your
Half-Life.
notes.
Thank you.
Okay. All right, nuclear chemistry, surprise, surprise, involves the nucleus of an atom. All right. We're not going to really be looking at electrons and what electrons do. Okay, we're going to put a pause on that. What I will say, this is the last week that we're going to unpack nuclear chemistry. Pretty much everything we do after fall break will be with electrons and bonding and just those kind of stuff. But we're going to wrap up nuclear chemistry right now. And then once we come back, we probably want to address it again, probably ever. We'll probably be done with it. All right. So what we're going to be looking at is protons, neutrons. Looking at protons and neutrons. What do they do? So when you have an unstable atom, what is it going to kick out? Okay. How do we annotate it first? So before we can actually start predicting what's going to be forming, we have to write those annotations out first. We did this in that simulation a few weeks ago, where the symbol would be the letter shown, this top number would be the mass, and then the bottom number would be the number of protons. So hopefully that rings a little bit of a bell, that atomic simulation we did where you created carbon, and then you made it unstable, and then you threw in some electrons, starting to talk about those ions and isotopes. So this is the generic formula, where Z is your number of protons, A is your mass, your atomic mass, so it's protons plus neutrons, and then X would be your chemical symbol. Okay. The problem with Schoology is that it's very difficult to write the annotation of elements like this. So like carbon-14, I'll write down here. Carbon-14 has 6 protons. So if we were to write it this way, all right, this would be true. However, this is very difficult to put in Schoology because you have 2 numbers stacked on top of each other. It's a big old headache. So instead, we're going to write it or annotate it the other way, which is C-14. Both of these things are going to say the same thing. 14 being your mass. You know what carbon is, so then you can find out how many protons it has by using your periodic table. I think that's it for now. I'm going to do attendance. I'll write that down. Am I not here today? Raise your hand. Lily, how'd your tournament go?
I wrestled twice. I lost, and then I got a head to the nose, and it pushed my nose out of place, and I had to get it cracked back into place. And it
That sounds great.
was bleeding everywhere. It's disgusting.
Did I even know?
Yes.
We're all here today. Fantastic. All right. Am I good here? Move on?
No.
No? Okay.
There.
Ryan, you awake?
Mm-hmm.
You sure?
Yeah.
Did you get to sleep over the weekend?
Yeah.
The amount of energy you have for this class is just like,
It's also late in the day.
well, like first few weeks of school, you were like up here, now you're like down here.
Yeah. 'Cause I hate school.
Sorry about that. Well, you know, I'm just recording what's going on right now, so now the whole world is gonna know that you don't like school.
I don't. I mean, I think everybody knows that everybody hates school.
Am I gonna move on?
Yeah.
All right. Don't write this down. Okay, it's got a great background. I'm just gonna talk about it. So, what exactly is going on when you think about the neutron? Okay, you have one of the four fundamental forces, which you probably have never heard about before. You have the strong force, which is what the nucleus is. You got gravity. You have electromagnetic force, and then you have the weak force. So the four fundamental forces explain how everything in the world works. The first one being the strong force. So when you think about the nucleus, it's got a bunch of protons in there. So the protons should push each other apart, but the neutrons keep them together. How that works is the strong force. All right, that's what holds everything together. Since there's a whole lot of energy in that force, okay, in order to break it, you release a whole lot of energy. If you do nuclear chemistry, you can either have an atomic bomb or you can have a nuclear power plant. That's where all that energy is getting released from. What are we going to do with it? Well, we're going to expand our vocabulary, all right? We know what protons are. It's got a mass of 1. We know what neutrons are. They got a mass of 1. No charge. Now we're going to look at alpha, beta, and gamma decay. But beta has 2 types in there. I'll get there in a second. All right. Questions are very welcomed. But if it's not on the slide or I don't explain it on the slide, it's not going to be on the quiz or test. So the first one being radioactive decay is alpha. So if a nucleus is unstable, right, wouldn't necessarily need to draw this picture out, but what is above it and below it absolutely is important. Okay, if this nucleus is unstable, right, it wants to get rid of some protons and some neutrons. So what does it do? Is this parent nucleus breaks apart and kicks out 2 protons and 2 neutrons, and now becomes a more stable nucleus. So the parent kicks off whatever else is making it unstable, and then the daughter nucleus is then made, and you have a helium or an alpha particle getting kicked out. This little small right here, this little letter, is the Greek letter alpha. It just looks like a fish. So what you can do is you'll see on your homework, right, when you're doing this, you can either write this as helium or you can write this as alpha. So I'm going to do the same problem using both, and we're going to see what I mean by that. All right. Morgan, how much do you remember about logs and exponentials? Do you remember what a log is? Is that word even like jogging your memory somewhere? Okay. Uh-oh. All right. Someone says we're going to do some really easy math on this part. The hard math will come later. All right. I'll give you a moment for that first. The bottom 2 below it are some examples we're going to do. And then you'll be like, okay, this isn't that bad.
I think we were starting to learn about it when we got into quarantine.
That would make sense.
Yeah.
It's usually second semester, midway through second semester. All right. What I'm going to do for you is on the homework, I will tell you what the element is and what the decay type is. You predict what was formed. All right. So like this one down here on the bottom right. Okay. I will say a atom of polonium goes through alpha decay, what does it produce? Evan, you ready?
I do believe so.
You do believe so. Okay. Top number up here. Actually, I'm just going to slide down a little bit. Can I be there? Is that okay for everybody? I'm just going to rewrite this a little bit bigger. We got 210 polonium, and it's got 84. Good there?
Mm-hmm.
Goes through alpha decay. We're going to kick off 2 protons and 2 neutrons. What will be formed? All right, here's what you think they're having. You're like, okay, this is actually easier than I thought it was going to be. Throw an equal sign right here. 210 equals 4 plus what?
206.
206. So my mass wasn't created or destroyed, right? You can't do that. What you can do, though, is you can change where it's at. So if I started with 210, I have to end up with, in total, 210 on the top. Does everybody see that? Not too bad? All right, Evan, how many on the bottom part? 84. Kick 2 protons out. How many protons we have?
82.
82. What element has 82 protons? Oh, every day you're going to need that periodic table
I
out.
have a
Caught him sleeping.
82.
Yep, what element has 82?
Lead.
What's the atomic symbol for lead?
PB.
PB. All right. How hard was that? Very. So deplorable. You're going to be scared, shaking in your boots doing the homework?
Yeah.
Okay. I give you the element on your homework. I tell you what type of decay it is. You predict what's going on. All right. Treat this as an equal sign. And there's just 2 simple math problems. That's it. Okay. Good here? Any questions? All right, now we're going to do stuff where hopefully maybe you're going to scratch your head a little bit. Beta decay. What happens if a neutron turns into a proton?
You add charge.
I just said a neutron turns into a proton.
It blows up.
No, you just
You
change
need to
the
high
element
energy
by
electron.
1.
So let's think about this. How does a neutron turn into a proton?
It's positively charged.
It's splitting into a positive side and a negative side. So in beta decay, either a neutron or proton is what you start with, and it flips to its other constituent. How does that work? Think of a neutron. Take a neutron. It splits into a positive side and a negative side. So now, we talked about all atoms made up of protons, neutrons, and electrons. What are protons, neutrons, and electrons made up of? Has anybody ever thought to ask that question?
Quarks.
Quarks. Quarks, gluons, and God particles, and a bunch of other stuff that we don't talk about in this class. So what I'm going to say is, when we think about beta decay, either a neutron turns into a proton, or a proton turns into a neutron by changing whatever's happening underneath the hood. We will not unpack that anymore. All right? If you're interested about quarks and partial charges and everything like that, have fun. Google search, go down the rabbit hole. Okay. What I'm going to say is, if an atom goes through beta decay, all right, what is going to happen? And then very specifically, you have beta plus and beta minus decay. Beta being this Greek symbol right here. Looks like a B, right? It's not really beta. Okay. But the only thing I did, just to make sure you're not confused too much, positron emission. Uh-oh. Needs to be calibrated. Emission. Let's try that again. E-M-M-I-S. I know it doesn't look like it. That's supposed to say emission. All right? To not confuse you, if I say beta decay, I mean beta minus decay. If I say positron decay, I'm telling you very specifically a positron was kicked out. So everybody knows what an electron is, or at least you should at this point. If you don't, you're really good at guessing. What happens when a proton turns into a neutron? It kicks out this thing called the positron, which is not a proton. It's a positively charged particle that has no mass. It is the opposite of an electron. Go ahead and chew on that for a second, Evan.
Ha ha.
There's no joke there.
I get that. I'm just trying to think. What? Okay.
Okay? Let's do these two down here on the bottom, and let's keep on moving. We good here? Morgan, you good? I guarantee you didn't do this in ICP. This is brand new stuff for you. Ooh. Lauren, you good? Cool. Lily's already out cold.
We all looked.
Okay. All right, let's do these two examples. The one on the left is beta decay. The one on the right is positron emission. So let's try it out. I'm going to rewrite this one just a little bit bigger. Iodine 131 has got 53 protons. Kicks out a high energy electron, or beta decay, and gives us what? Alex, you ready?
Yeah, I think so.
Okay, on the top side, does my mass change at all?
No.
No, so we're still left with 131. What about the bottom side?
Yes.
What's the bottom side going to be now?
It's going to be xenon, or 54.
54, okay, absolutely. Because 53 equals 1 minus what? Well, 54 minus 1 equals 53. Okay, that's just that simple math all the way across the bottom. You good, Caden? All right, how do we know it was xenon?
Because that's 54 is the atomic number for xenon.
Absolutely. Okay,
Wait, does that mean that the iodine just became xenon?
absolutely.
Okay.
But it kept its mass, right?
So that's
Yep.
why it's like dangerous. And
So
radioactive.
polonium,
Yeah.
when it goes through radioactive decay, turns into lead. Iodine 131, when it goes through radioactive decay, what does it turn into?
Xenon.
Xenon. Cool? Ready? Yeah, Lauren?
Why on the last one did we like actually subtract from it? Like on the alpha one, did we like actually subtract from it? This one, we added to it.
Well, we think about it as a math problem. We didn't know what it was going to do. So 53 equals negative 1 plus x. Where on the last one, we had 4 and 2, both positive numbers. This one now we can now have a negative number. Follow me there? Okay. So if you, some people, just to help get them straightened out, right, they'll write out this little math problem right here, and they'll just solve from there. Does that answer your question? I feel like I did not a good job doing that.
No.
Explain it. Okay. All right, let's do it the other way. Let's take oxygen. Let's put it through positron emission. Johnny, I'm coming to you.
Okay. So we're doing it back.
Oxygen 15 goes through positron emission. What's my mass going to be?
15.
15. Mass doesn't change at all. What's my charge, though? All right, it's not my charge. My number of protons.
Is it 7?
Absolutely. Because 7 plus 1 gets you 8. So what element do I have?
Nitrogen.
Oh. Phosphorus. Right? That's not phosphorus.
Mm-mm. Nah, you looked at mass.
Oh, potassium.
No.
7.
7.
Number 7. Oh, nitrogen.
Nitrogen, okay? The bottom number tells us what element we have. The top number tells us mass. Here's how you type this in the homework. Here's how you type this in the homework. Okay? I very specifically said in the instructions, but make sure we're all here. If you tell me what element you have, I know you know how many protons we need. That's not the thing I want. All I need is tell me what isotope you have. So on the homework, if this is one of your questions. Iodine goes through beta decay. What does it turn into? Xenon 131. Okay. I tried my best to figure out how to get Schoology to do these kind of inputs, and it's just not quite there yet. Okay. Yep.
Do we have to put the dash?
Yes.
Okay.
So this one would be N dash 15.
Okay.
Cool. Hey, Hudson, 4 on the floor, please. That breaks chairs. Any question here? Kate, you good?
Yeah.
Come to you next.
Okay. Yes, sir.
Travis sucker.
Yes, sir.
Absolutely.
Yeah.
Ooh, I almost about to hit that.
Good catch.
Gamma decay.
Oh.
Third type of decay. We have alpha. We have beta, which really has 2 types. Now we have gamma. You ready?
Yeah.
Gamma releases just pure energy. Does gamma have any mass or charge to it?
No,
No. So what happens to it?
just stays the same.
Stays the same. Woo hoo hoo hoo! Hot dog.
Hot dog. Hot diggity dog.
The only difference is if something is unstable to where it wants to release gamma radiation, right, it'll go from an excited state to a very stable state and only release that energy. Alpha's big, beta's medium, gamma's small. So now maybe we can really understand, or at least unpack a little bit more, why alpha particles, which are big, try to go through stuff and they just can't. Beta is a little bit smaller and can wiggle in between stuff, like wood and paper. But gamma, since it's super small and it's just energy, it wiggles in between everything, including your DNA, breaks it in half, rewrites your DNA, which is why if you stand in front of gamma radiation, you'll either die or get cancer. So the Hulk, when he was in front of that gamma radiation, should have just melted on the spot. You okay, Brian?
Why is there an asterisk about
The asterisk just means that it's excited state.
Really excited.
Yeah, you're ready to roll, Brian. You're so happy, man.
Yeah.
All right, we good here?
Mm-hmm.
No? What do you need, Brian?
Oh, will you go back to the beta notes?
Yeah.
Because I didn't write it
Do you need the examples or what's up there?
down. Oh, just what's up there.
Okay. So what we're going to do now is we're going to look at how do we take this stuff and we look at the actual mathematical model of when stuff decays. Right. When we look at dinosaurs, how do we know how old a dinosaur is? It's not because...
When they died.
You okay, Brian?
Yeah.
There's just so much not forethought in that and what you just said. That doesn't make any
Well,
sense.
when they died, you can tell how old they were when they died. When they died. Like not here.
Let's try this again.
They died.
All right. If we look at nuclear chemistry, you can predict how old something is. Alex, you good?
Almost.
Oh. You can predict how old something is based upon how quickly it decays. Evan, you okay?
No.
No?
I slept through
Can we
my
just all
alarm
sleep?
twice this morning, and I'm really mad about it. And I'm still tired.
Silly. Funny.
All right. Here's your mathematical formula.
After I hold that, I just read the formula.
These are your notes. If you have no clue how to do it after today, that's on you.
So we don't have to write this down if we don't want.
These have always been your notes. If you don't know how to do it after today, that's on you.
Is that 0? Is that?
No.
Oh.
That's
It's a
0,
zero.
I think.
It's
Yeah, because it's a 0.
This is a function. N being the number of n sub naught, so this is n naught. Okay. This is your original, or your starting amount. N is your ending amount. So what we're going to do is we're going to look at when something radioactively decays. It turns from one thing into another thing. How fast, though? Not everything decays at the same rate. Some things do it very, very quickly. Some things take a very long time, like carbon, which is where carbon dating comes from. All right, I'm going to do the shortcut method. All right. And then we're going to try to attempt using this actual formula to predict things. The problem is that some of you have learned that. Oh, sorry. Maybe one of you have learned this math. The vast majority of you, this is going to be brand new math for you. All right. In either case, we're going to do it. All right. If I started off with a time, we're going to call this time. We're going to call this grams, so that's the amount of mass we have. At time equals 0, how much do I have? 8 grams. Right. Every 5 hours from there, we're going to hit a half-life. So a half-life is the time required for half the atoms in a sample to decay. So after 5 hours, Lauren, you ready? Hardest question of the day. What's half of 8?
4.
Man, this is hard stuff. Follow me there? All right, after 10 hours, 2 half-lives have gone. What's half of 4?
2.
Man. After 15 hours, what's half of 2? Man. All right. We can predict stuff if it follows nice and pretty on those half-life marks. What happens if it doesn't, though? Well, if in 6.5 hours, how much do we have left? That's when we're going to have to use this thing. All right. So for this first problem right here, after the first half-life, 5 hours have gone by. Second half-life, 10. Third half-life, 15. Okay. You can kind of use this model to predict the easy ones. So on your homework, I believe I gave you half easy ones, half using the formula. We're just going to keep going though. Yeah, I'm gonna before I shoot myself in the foot and explain too much, we're just gonna go for here right now. What questions do we have for this one? Because I'm gonna do a next example and then seeing if we understand it as a class. So let's make that connection between what we just did and what we're doing now. We have plutonium-243 goes through alpha decay. That turns into uranium-239. Plutonium to uranium, that is used in nuclear reactors. So if we go to a nuclear reactor and they hand you a plutonium pellet, 1, run away with it because it's worth a couple $1 million. 2, it's not very big. So that plutonium, when it is used and it decays, it turns into uranium-239. Turns into a new element. So 1 half-life, we go from 8 to 4. 2 half-lives, we go from 4 to 2. So on and so forth, and then we keep on going. All right. We're going to use this thing soon, but not for the next example. There you go, Brian. Figure that out. Yeah, Alex?
Is 25 grams.
That's it.
How did you do that?
Because you do 100 divided by 2, and then do 50 divided by 2.
So let's plug and chug and let's check this out. So we have half-life. We have the time elapsed. And then we got the amount of mass or amount of grams we have left. So Alex, help me out. That time equals 0. 0 half-lives. How much should we start off with? 100 grams. How long is our half-life?
29 hours.
29 hours. So after 29 hours, after one half-life, this thing gets cut in half. So how much do I have?
50.
50. Everybody good there? You good, Mark? Okay. After two half-lives, how many hours have elapsed?
58.
58. 29 plus 29 is 58. And what's half of 50?
25.
25. So after two half-lives, or 58 hours, we have 25 grams left over. Did you see that now, Johnny?
Yeah.
Okay. I'm now going to plug this into that mathematical model. Use my calculator. We got n equals, ends up not, 1/2 t divided by t 1/2. Okay. If I do this correctly in my calculator using that formula, we should get 25. N is how much we're figuring out is left over. Alex, help me out again. How much did I start off with? How much did I start off with? What was my original amount?
Oh, for this problem?
Yeah.
100.
100. 1/2 to the power of t. How much time has elapsed?
21.
No. How much time?
58 hours.
58 hours divided by, and what's my half-life? 29, right?
Yeah.
So t being the time elapsed, t 1/2 being your half-life, we could just, and here's why I love these calculators. All right. On a side note, if you're ever going to go buy a calculator, at some point, if you're going to go to college, you need to buy one. This is the one, V1, I recommend. Graphing calculators are great, but you can't use them in college. The reason being is because it's so easy to cheat on them. So if you end up going to college and taking a math or a science class, they will only allow scientific calculators. I really like this one. All right. So I'm just going to punch this in. I'm typing 100 times 1/2 to the power of 58 divided by 29. All I did was punch it in my calculator, and it did all of that math for me. I get 25. Okay? Good here? Good, Caden?
Yeah.
Okay. That didn't seem like a very confident yeah. Brian, you good? Okay. We're zombies today. Even Evan's not saying much. All right. Here's what I'm going to do. I'm going to pause it right here because this is where the other class stopped. So instead, what we're going to do is we're just going to switch gears. I'll give you like 10 minutes to work on that homework, start on the homework. All right. That way, if you got any questions, you can let me know. And I'm not beating you to death with notes because Morgan already wants to go to sleep. Evan's already asleep. Lily already took a nap.
I think Evan is asleep.
No, he's not.